Now, the first factor that affects the rate of the reaction is the surface area of a solid reactant. If we use smaller pieces of any solid substance that is in the reactants, we will have a larger or higher rate of the reaction overall. This is an example. The reaction of marble, CaCO3, calcium carbonate, with hydrochloric acid. The products are CaCl2, H2O, and CO2. Now, we can use CaCO3 solid, large pieces, or small pieces. The observation is, if you use smaller pieces for this reaction, the rate of the reaction is higher. The reaction will end faster and it will take place faster, and we will observe the loss of the mass of CaCO3 faster, or the gas, we will observe the production of gas also faster. If we look at this graph, it shows the reaction rate if we use smaller pieces, and the reaction rate if we use larger pieces. This curve shows smaller pieces or smaller chips. We can see that the curve here is steeper. The curve in red color, smaller chips, is steeper than the curve in blue color. That means that the reaction starts faster. Okay, if we use larger chips, the rate or the curve is less steeper, so the reaction is slower. And also, you can see that the reaction at this place, the curve starts to be horizontal, so the reaction has ended here within approximately 4 minutes. The other reaction is ending up here approximately at 5.5 minutes. So this shows that smaller ships are affecting the rate of the reaction by having a higher rate of the reaction. And why does this occur? Because of the collision theory of the reaction or of the reactants. Okay, these two pictures show another reaction, the reaction of iron atoms and oxygen molecules, using larger chips and using smaller chips or smaller pieces. If we use a larger piece of iron, the oxygen molecules can only colloid with the surface area of the iron, and it can only, we can say that the oxygen molecules can only see these atoms of iron which are at the surface. Okay, if we use smaller pieces of iron, oxygen molecules can see or can reach more atoms of iron because they are on the surface, because we have here larger surface area with smaller pieces. So we can explain the rate of the reaction when we have smaller chips or smaller pieces of the solid reactant, because we have larger amount of atoms or molecules that can colloid with each other. So we have more frequent collisions between the reactants. These collisions, they can cause the reaction to occur between the two reactants. So this is for the first factor. The second factor that affects the rate of the reaction or of any chemical reaction is the concentration of the reactants. The concentration of the reactants, for example, if we are talking about this reactant, which is an aqueous solution, okay, for this reactant we can use lower concentration and higher concentration. If we use low concentration or lower concentration, lower concentration, we will observe that the reaction is or has a lower rate, and the reaction will take more time to end. And if we use higher concentration, we will observe that we have higher rate and the reaction will take place faster and will end up faster. If you, for example, double the concentration, for example, if we use for the lower concentration 0.5 molar concentration, and for the higher concentration, if we use 1.0 molar concentration, so if we double the concentration, you will observe that the reaction will take place in half the time. So if we double the concentration of the reactant, we will observe that the reaction will take place by half the time of the one with the lower concentration. This is clear at this curve. Okay, the red curve is for the higher concentration, the blue curve is for the lower concentration. The red curve, you can see that it's more steep because the concentration is higher, 1 mole per decimeter cube of the acid. And the blue one is less steep because it's for the lower concentration, 0.5 mole per decimeter cube of the acid. Okay, as you can see, it's the concentration is doubled. Okay, the one with a higher concentration, the curve starts to be horizontal at this point, so it took approximately 55 seconds for the reaction to finish. And the one with lower concentration, it starts to be horizontal or constant at this point, so it took 110 seconds. So you can see that the time is double or is half. If you can, if you compare between the higher concentration and the lower concentration, the time is double. And if you are comparing vice versa, so the time is half. So if you double the concentration, it will take less time. If you double the concentration, the time will be half of the one with the lower concentration. Also here you can see the apparatus for some reactions that we can use this apparatus to measure the volume of the gas that is going out from any chemical reaction. This is for the reaction of magnesium and hydrochloric acid, the reaction that we have just discussed. Okay, we have a stopper here, okay, or any timing machine, you can use a watch, any timing machine. Okay, this is a closed system for the reaction to take place in this flask. Okay, and there is a place where the gas can go out, and it goes out in a syringe, and in this syringe you can measure the volume of the gas that is going out. By measuring the volume of the gas, you can draw this graph for the chemical reaction, for the rate of the chemical reaction. This is one of the observations that we have already discussed in the previous video, that if we have a gas product, we can use this gas product, the volume of this gas product, in order to measure the rate of the reaction, because it's easy to observe or to measure the volume of the gas. Okay, now let's explain why the reaction with high, or why when the reactants are in higher concentration, the reaction will be faster. If we look here at this, okay, if we look here at this, or at these two figures, okay, this is by using a dilute acid, and this is by using a concentrated acid. If you use a dilute acid, you will not find so many collagens between the magnesium and the acid because we only have a few molecules of the acid. But when we use a concentrated acid, the collisions between particles of the acid and of the magnesium are more frequent. So more frequent collisions will affect the rate of the reaction. So the explanation of the rate of the reaction, why is it higher when we use a concentrated acid or a concentrated reactant, whatever the reactant is because the collisions between the reactant molecules are more frequent, and more frequent collisions will cause a higher rate of the reaction or faster reaction. The third factor that affects the rate of the reaction is the temperature. You can do any chemical reaction at lower temperature or at higher temperature. If you do the reaction at lower temperature, the rate will be low. And if you do the reaction at higher temperature, the rate will be high. Now, let's take an example. Example of the reaction of sodium thiosulfate, Na2S2O3. This is a solution, a separated solution, with another solution of HCl. Mixing up these two solutions, I will show you within a minute the figure on the book. If you mix up these two solutions, you will have NaCl, aqueous, and S, solid, which is a yellow solid, SO2 gas, and H2O, liquid. Okay. Now, the observation that you have to see in this reaction is the formation of the yellow solid sulfur. They, in the book, they are describing a way to see or to observe the formation of sulfur. You can see here we have two solutions at first. The solution of sodium thiosulfate here in the beaker. There's a paper underneath the beaker which has an X drawn on it. Okay, if you look through the beaker, you can see the X because the solution is transparent, clear and transparent, and this is the hydrochloric acid, diluted acid of hydrochloric acid, HCl. Okay, also it's a clear solution. Now, by starting mixing the HCl to the sodium thiosulfate solution, by the time you will observe that you cannot see, or you will start, the X underneath the beaker will start to disappear. The disappearance of X means that sulfur, the yellow solid sulfur, is being formed because it's making the solution to be unclear solution. Now you can measure the time by the first second you start pouring the HCl over the sodium thiosulfate, and by the time to the time that the X starts to disappear completely. Okay? Now, if you use a solution of sodium thiosulfate with a higher temperature, if you heat this solution and use it, you will observe that this reaction is taking place in less time. So that means that the temperature is affecting the rate of the reaction by making it higher speed or higher rate, or a faster reaction. If you raise up the temperature of the chemical reaction, it will be higher it will have a higher rate or it will be faster reaction. Why is that? We can also, okay, we can also explain the temperature of the reaction using higher temperature of the reaction by using the Collision theory. So these two figures shows lower temperature and higher temperature. By the you know from the kinetic energy that if any substance have higher temperature, so the particles will move faster. The faster moves of the particles, that means that they will collide more frequent with each other. More frequent collisions with each other, that means, as we said before, a higher speed reaction or a higher rate reaction. So that's why reactions with higher temperature, they will have higher speed because they will collide more with each other because of the higher kinetic energy of the reactants or of the particles inside this reaction.